Good morning to all present and good evening to you, Dr. Hadke. Starting with the session today, BioX-based synergizing STEM is on a mission to bring interdisciplinary learning at the central stage, where learners, high career seekers, researchers, and innovators are prepared for the opportunities that are provided in the 21st century. So, beginning with the session, thank you, Dr. Hadke, for joining us and giving us your time. So before we begin, I'd like to give our audience a brief introduction about you. So Dr. Shreyash Hadke is currently a postdoctoral fellow in the School of Material Sciences and Engineering at the Northwestern University. His research focuses on optoelectronic analysis of semiconductors for photovoltaic cells. He received his Ph.D. from Nanyang Technological University, Singapore, where he gained experience in tuning novel semiconductors for renewable energy through chemical modification towards targeted applications such as photovoltaics and photocathodes. Thank you for joining us today and giving us your time, and we are eagerly waiting for your session today.
Okay, thanks. Thanks for the introduction. Is this visible?
Yeah, it's visible, sir.
Okay. So I'm going to talk about basically preparing for a research career in interdisciplinary sciences. And a brief introduction. So I did my bachelor's in metallurgy and materials from VNIT Nagpur, and then master's in nanoscience from IISc Bangalore, and a PhD in material science from NTU Singapore, and then a postdoc in chemical engineering at Purdue University. And now I'm a postdoc in material science at Northwestern University. So talking about interdisciplinarity, I would basically just use my own experience here. So I've been working on solar cells during my PhD, and just to give an idea about how interdisciplinary this field is, I'll just talk about how solar cells would be interpreted by people in different fields. So let's say, for example, for someone from energy systems, right, how would they look at solar cells? They would probably look at solar cells as this thing that gives us extra power when people don't really use it in the afternoon, right? If you talk to an electrical engineer, they would probably look at solar cells as just a circuit element. If you look at electronics, they would probably go a little bit deeper and say that it's a diode that acts as a constant current source and has a shunt and series resistance and a voltage across it when exposed to light. When you come to materials, people will start thinking about what two semiconductors would you put together to get the photovoltaic effect, and how do you make these heterostructures, what metals do you align towards semiconductors, and how do you make those materials, and so on. And for someone from chemistry, it would be more about how do you synthesize these things and what's the reaction pathway when you're trying to make, let's say, one of these materials. And then let's say from someone from physics, they would delve even deeper into it and ask questions like what happens when light impinges upon or light is absorbed by a semiconductor. How do the electrons and holes that are generated behave on a nanoscale and on a nanoscale regime? So those are all the different ways in which different people would look at solar cells. In my lab during my PhD, we were basically working on these 4 areas somewhat. And this takes me back to like the first conversation that I had with my PhD supervisor, where she asked, we have the spectrum of available projects that delve into chemistry, device physics, material science, and what are you more interested in? And this was kind of my reaction to it. So I guess that's kind of important if you want to work on an interdisciplinary field, so that you should try not to limit your scope. So just be curious, I guess, about different fields. And for example, I did not have any experience in device physics, for example, but that is something that I just enjoyed the most during my PhD. So the good thing about interdisciplinary research is that you get to experience a lot of different fields, and you have an opportunity basically to explore different things and figure out what you really like. I'll talk a little bit, like just 2 slides, about my actual work. So, as I mentioned, I worked on solar cells. So I was working on these copper, zinc, tin sulfide-based solar cells. This is what copper, zinc, tin sulfide looks at an atomic scale. So the yellow atoms are copper, the blue ones are zinc, the green ones are tin, and the black ones are sulfur. So what happens is when sunlight falls on this material, we form electrons and holes in the semiconductor, and they kind of travel or go through the external circuit to power whatever load we put across it, right? So what basically happens in the real world is that in this material, the copper and zinc kind of don't like to be in the correct place, and this goes into thermodynamics, that at finite temperatures, different atoms move around. So that's another angle that comes in. So because of this, what happens is we kind of form something that we call defects. So it's a copper goes where zinc should be, and the overall charge at that side would not be zero. So in the previous example, we saw that when electron and holes are formed, then they go through the external circuit. But here, they would get attracted to these charge defects, and they would not go through the external circuit, and there will be no light, which sounds a bit dramatic, but that's what physics is. From a more electronics perspective, basically what would happen is most of the electrons and holes would still go through the external circuit. It's just that some of them would be trapped in these defects. So what would happen is you would get smaller current density and smaller voltage from the solar cell, right? So what's the solution to this? A very intuitive solution is, if copper and zinc like to exchange their positions, then just replace that zinc with something that's bigger or smaller. So for example, here, if you replace the zinc with a bigger cadmium atom, which is just physically larger, then the chances that a copper and cadmium would swap positions would be smaller. So that's the material solution to it. Now, in this slide, we are not going to go into any details, but how do you do that from a chemistry perspective? So you could take all of these organic salts, put them in a solution, and drop cast them, spin coat them, and heat them so that you are left with copper, zinc, cadmium, tin, and sulfur. And you can change the concentrations of these two compounds to basically change the fraction of cadmium that replaces zinc. We are not going to go into details of this at all, but what we've basically found is that when we do this thing, when we add this cadmium, then the energy that is required to form this defect increases. So for anything that requires more energy, it would be less likely to form. So essentially, when we make a more perfect material, when we start adding these larger cadmium atoms, so that's what this plot shows. This plot is quite cool. So if we have copper, zinc, tin sulfide, which was this, and the copper, cadmium, tin sulfide, which is what we make by adding cadmium, then we can actually measure the time for which these electrons and holes are present in the material. And we do this using something called time-dissolved photoluminescence. So here, we shine light on the sample, so that is 0. We shine light, and then we turn light off at time is equal to 0. And then we can measure how long the electrons and holes that are generated stay in the semiconductor. So if we have less defects, then they will stay for longer. So which is what this is showing. The x-axis here is time. So when we put these cadmium atoms, we observe that these electrons and holes stay longer in the system. And then finally, from let's say an energy perspective, what that means in a real solar cell is that the efficiency with which we convert solar energy to electricity increases. So for example, in this copper zinc tin sulfide, you can convert 5 to 7% of incident light to electricity. But when you replace zinc with cadmium, that goes from 6 to 11%. So just like a factor of 2 improvement in the solar cell performance. So yeah, that was just a very brief way to describe my research work. So we'll now go more into what interdisciplinary research is and how we should approach it. There are two ways in which we should not approach it. And those are these. So there are these different views at different ends of the spectrum where people are like, oh, interdisciplinary goal-oriented research is the future and fundamental research has limited applicability in the real world. And you'll hear many people saying this, especially in, let's say, coming from more commercial side of things, and just ignore them. And then there would be people who are deep into science, and they would be like, okay, interdisciplinary research is just engineering, it's not real research. And I'd say ignore them too. There's like a happy medium, and which is, at least in my opinion, more true. It's that we need fundamental research to design interdisciplinary, goal-oriented engineering solutions to real-world problems, right? So if, let's say, someone asks you or if you are interested in interdisciplinary research and sometime it bugs you whether you're doing science or engineering, just remember that you are somewhere in the middle and that's okay. Right. And this is like the last part of the presentation where, just based on my experience, I've kind of put together some do's and don'ts. And the green part here, like the middle part, is the most important. It's when you're in an interdisciplinary field, such as, let's say, solar cells, it's very easy to not have any expertise. It's kind of very easy to just know a little bit about a lot of things. My main, let's say, suggestion would be to not fall into that trap. That is, don't be a master of none. Like, have at least something that you have a reasonable expertise in. So it could be, so let's say, for example, in my particular case, in solar cells, I could have an expertise in just, let's say, synthesis of materials or deposition of materials or device physics or semiconductor optoelectronics or just simulations, right? Or just solution chemistry and so on, right? So you should first know all of the things that you're involved in, but there should be at least one subfield that you are an expert in. And the reason for that is here. So it's because you have to be a node. So interdisciplinary research is like a network where everyone wants to work with everyone else because people have different expertise. So people will only want to work with you if you have an expertise. So be a node. So for example, in this network, you see that different circles are connected to different other circles. And here's an example of, let's say, from my PhD. So this is a paper that I was a co-author in, and just looking at the title, it's very clear that I don't have an expertise in this. So why am I in this? It's because my supervisor was a good node here because they wanted to do some optoelectronic measurements that our lab was good in. So they kind of approached my supervisor, and then I was the node for my supervisor because she knew that I was good in our group for that. So what you want is to be like an expert at something and use that as a node to develop interdisciplinary projects. The second is know your strengths. So I am not very good at just organic chemistry, solution chemistry, and so on, but I'm really good at let's say optoelectronics, like more physics part of it. So here are a couple of other papers that I was a co-author in, and my contributions in this are purely from electronics perspective. So since the main authors of these papers considered me to be a decent node for electrical measurements, so that was my strength. And if you know that, you can approach people using that and basically develop your network. The third is kind of all these three things I think go together. So collaborate a lot. So during my PhD, like for my first author papers, you would see that there are all of these authors in different papers. That's because we collaborated with different people because they had their own expertise. And they were basically they are experts in what they do. So they are effective nodes for what they do. And here the most important thing from an individual perspective or from your perspective would be to learn their language. So for example, like Professor Carter and Sai from Princeton, they did simulations and they use a completely different language to talk to each other. And if you, let's say, go into a meeting with them not knowing that language, it gives an impression that you don't really know what you're doing, which is very easy, which is a very likely trap that one falls into in interdisciplinary research. Is basically you just don't know what other people are doing, even in your own papers. So try not to let that happen. So learn the language that different people in different fields are using. And finally, these two kind of go together, because interdisciplinary research is kind of goal oriented. Because like the reason that you have to bring different fields together is to find solutions to problems, right? And it's very easy to work on problems that don't really exist. So, and this is also a common thing that I've observed in like just some of my colleagues, I guess. So yeah, don't be a solution in search of a problem. Like think about whether a problem is worth solving, because right now interdisciplinary research is a hot topic. So it's very easy to just start doing something, and it basically doesn't make a lot of sense. And target the right audience. So you are solving a problem, right? So you need to know exactly what audience are you targeting with that problem. So those are like last two suggestions. So yeah, that's all I had from my side, but I'd be happy to discuss this further.
Thank you, Dr. Hadke, for sharing this. Since I'm also stepping into interdisciplinary research, this was really eye-opening. So one of the questions I had from you was that like you had a set network going into your PhD and everything, but you discovered interdisciplinary after you entered into PhD. But if somebody like I am going into my master's right now in biotechnology, and I want to focus between the molecular biology and the current industrial applications of biotechnology, how do you suggest that we go create a network that can help us pursue an interdisciplinary research or a project?
Right. So basically, you would have to do it one step at a time. How these things work is you find a node, and that usually is your supervisor to begin with. And they basically open different doors for you. Again, that's just the role of a supervisor. And then it's up to you about which kind of direction you lean more towards. And basically just go from there, I think.
Okay. Thank you for that. And I really enjoyed your session, and it was, really helpful to plan my future and and it also aligns with our BioX space mission very, very clearly, because that is what we're trying to reach. So thank you for giving us your time. And I hope we can have future sessions with you. So thank you.
Okay.
And
yeah.
Thank you for
Thanks.
doing this. Okay.
Yeah.